electronic theory of valency. In this module, we will learn about the electronic theory of valency. A chemical bond between two atoms can form only if they come close to each other. When two atoms come close, each may affect the electronic arrangement in the other. The electrons in the inner shells are tightly bound by the nucleus and so remain almost unaffected. However, the valence electrons are relatively loosely bound and are therefore available for bond formation. The explanation of the formation of a chemical bond in terms of valence electrons is known as the electronic theory of valency. We can understand the formation of a chemical bond by studying the electronic configuration of noble gases which normally do not form any chemical compounds. The noble gas atoms, except those of He, have 8 electrons in their valence shell. G. and Lewis proposed that having 8 electrons in the valence shell makes the electronic arrangement especially stable, and that is why noble gases are chemically inactive. We can infer that the other elements, which do not have 8 electrons in their valence shell, try to achieve the stability of the noble gas configuration by forming chemical bonds. The group of 8 electrons in the valence shell is called an octet. Generally, an atom tends to form bonds until it has 8 electrons in its outermost shell. This is called the octet rule. Bonds in H and Li compounds are exceptions to this rule. An H atom, which has only the K shell, can achieve a maximum of 2 electrons, called a duplet, as in He. Lithium also forms bonds by achieving the electronic configuration of He. In general, in the formation of stable entities, every atom tends to achieve the electronic configuration of the noble gas nearest to it in the periodic table. The work of G. and Lewis and Walter Kossel led to the identification of 2 types of chemical bonds: the Ionic Bond or Electrovalent Bond and the Covalent Bond. The 2 types of bonds arise due to the 2 different ways in which an atom can attain the stable configuration of a noble gas. Ionic Bond, Part 1. In this module, let us learn about the ionic bond. One way in which atoms combining to form a compound can attain a noble gas configuration is by the transfer of electrons from one to the other. One element loses electrons, which the other element gains. In this process, an atom can lose or gain a maximum of 3 electrons. Metal atoms, being electropositive, acquire the configuration of a noble gas by losing their valence electrons and forming cations or positive ions. For example, lithium loses 1 electron to form lithium-1 plus ion. Sodium loses 1 electron to form sodium-1 plus ion. Magnesium loses 2 electrons to form magnesium-2 plus ions. Calcium loses 2 electrons to form calcium-2 plus ions. Non-metals like nitrogen, oxygen, Fluorine and chlorine, being electronegative, can complete their octet by gaining electrons and forming anions or negative ions. For example, nitrogen gains 3 electrons to form nitrogen ion. Oxygen gains 2 electrons to form oxygen ions. Fluorine gains 1 electron to form fluorine ion. Chlorine gains 1 electron to form chlorine ion. However, elements like C, 2,4 or Si, 2,8,4 cannot attain the noble gas configuration by the transfer of electrons, as it would involve losing or gaining more than 3 electrons. Coasel proposed that the electrons lost by metals are gained by non-metals, leading to the formation of oppositely charged ions. And 2. The electrostatic force of attraction between the oppositely charged ions brings them close together, forming a bond. A chemical bond, formed by the transfer of one or more electrons from one atom to another, is called an ionic or electrovalent bond. Compounds containing only ionic bonds are called ionic compounds or electrovalent compounds. Compounds made up of a metal and a non-metal are generally ionic. The Ionic Bond. Part 2. The electrovalency of an element is the number of electrons an atom of the element loses or gains while forming an ionic bond. From the examples, it will be clear that the electrical charges are balanced in ionic compounds. Let us take some examples. The formation of NaCl. An Na atom, 281, transfers its outermost electron to a Cl atom, 287. This results in the formation of Na plus and Cl minus ions. Na plus has the configuration of Ne and Cl that of Ar, 288. The cation Na plus and the anion Cl attract each other to form an ionic bond. The formation of CaO. A Ca atom, 2882, loses both its outer electrons to form an O atom, 26. The Ca2 plus, 288 and O2 minus, 28 ions thus formed have the configuration of noble gases. These ions come close due to an electrostatic force of attraction to form an ionic bond. The formation of MgCl2. An Mg atom, 282, loses its outermost electrons to 2 Cl atoms, 287, each of which takes up 1 electron. Thus, an Mg2 plus, 28 and 2 Cl minus, 288 ions are formed. Since the 2 Cl minus ions repel each other, they approach the Mg2 plus ion from the opposite sides. Let us now learn about ionic solids. The Ionic Bond. Part 3. Ionic solids. The force of attraction between the cations and anions is so strong that ionic compounds form crystalline solids. In a crystal, the atoms, ions, or molecules are arranged in a definite three-dimensional geometrical pattern called a lattice. In an ionic crystal, the positions in the lattice, called lattice positions or lattice points, are occupied by ions. In the lattice of NaCl, each Na plus ion is attached to 6 Cl minus ions, and each Cl minus ion is attached to 6 Na plus ions. No Na plus ion is attached exclusively to any one Cl minus ion. So no discrete molecule of NaCl exists in the solid state. But on the whole, the same number of Na plus ions are there as Cl minus ions, and hence the formula NaCl. In the vapor state, however, molecules of ionic compounds do exist. Factors that favor the formation of ionic bonds. The formation of an ionic bond is favored by 1. A low ionization energy of the metal so that cations are formed easily. 2. A high electron affinity of the non-metal so that anions are formed easily. And 3. Large electronegativity difference between the metal and the non-metal, nearly 2 or above, so that electrons are transferred easily. We know that in the periodic table, 1. The elements on the left-hand side have a low ionization energy and low electronegativity. And 2. Those on the right-hand side have a high electron affinity and high electronegativity. So, the bond between an element from the left-hand side and another from the right-hand side of the periodic table is likely to be ionic. Part 4. Properties of ionic compounds. Ionic compounds have the following properties. They form crystalline solids. This is because the force of attraction between cations and anions is strong. They are hard and brittle. An ionic solid is hard because of the strong force of attraction between the oppositely charged ions. The lattice is, however, brittle. A large enough force applied on the lattice causes its layers to slide. 3. An ionic solid has a high melting point. This is because of a large amount of heat energy is required to break the lattice. Such a solid has a high boiling point. The constant temperature at which a liquid changes into vapor is called the boiling point of the liquid. In order to form vapors, the molecules of the liquid have to overcome intermolecular forces of attraction. This requires energy. In ionic compounds, even in the molten state, the force of attraction between oppositely charged ions is strong. Therefore, the ions require a large amount of energy to overcome this force and escape the melt. So the boiling point of an ionic compound is high. Ionic solids are bad conductors of heat. Conduction of heat requires mobile particles such as electrons in metals. Since ionic solids lack mobile particles, they are poor conductors of heat. They are usually soluble in water, but insoluble in organic solvents. Water is a polar covalent molecule with a small positive charge on H and a small negative charge on O. When water molecules come close to a crystalline surface, the negative ends of the molecules, O, pull the cations, and the positive ends, H, pull the anions. Generally, this is enough to separate the cation and the anion so that the lattice breaks. The separated ions get surrounded by a large number of water molecules. The water molecules surround the cations with their negative ends pointing towards the ion, and the anion with their positive ends towards the ion. The ions surrounded by the water molecules are said to be hydrated. Organic solvents, on the other hand, are either non-polar, that is, carbon tetrachloride and benzene, or only feebly polar, that is, ethanol and acetone. They do not exert a strong enough pull on the ions of an ionic compound. Hence, they usually do not dissolve an ionic compound. Ionic compounds conduct electricity in the molten state or in aqueous solutions, but not in the solid state. The lack of mobile charged particles in ionic solids prevents them from conducting electricity. However, on melting or in an aqueous solution, ionic solids break down to their constituent ions. The separated ions are free to move, and so the melt or the solution can conduct electricity. They undergo fast reactions in aqueous solutions. Chemical reactions involve the breaking and forming of bonds. The bond between a cation and an anion breaks, and the ions become mobile as soon as an ionic compound dissolves in water. The shared electron-paired bonds we have discussed so far comprise of one electron from one atom and the other from the other atom. However, there are also electron pair bonds in which both the shared electrons are provided by one atom alone. An electron pair bond in which both the shared electrons are provided by one atom is called a coordinate bond. The atom providing the pair of electrons for sharing is called the donor atom, and the one receiving the electron pair, the acceptor atom. Generally, the donor and acceptor atoms are parts of molecules or ions. The donor atom possesses lone pair of electrons, that is, the O atom in H2O and the N atom in NH3. Let us see two such cases. Formation of H3O plus ion. When an acid dissolves in water, an H3O plus ion is formed. Let us see how this happens in case of HCl. The O atom of H2O donates its lone pair to the H of HCl and forms a coordinate bond with it. An H atom needs to form only a duplet. The H atom in HCl obtains 2 electrons from the O atom. So, it has to leave its own electron with the Cl atom, leading to the formation of Cl-. Thus, H attaches itself to H2O as H+, forming H3O+. Formation of NH4+ ion. Ammonia, on reacting with an acid or water, forms an NH4+ ion. In these reactions, the lone pair on N in NH3 is donated to the H of the acid or water. Its duplet achieved, the H atom leaves its own electron with Cl or OH. Chlorine and OH become negatively charged, and H+ attaches itself to NH3 to form the NH4+ ion. Can contain more than one kind of bond. Many compounds contain more than one kind of bond. Some common examples are as shown here. Alkalis. Soluble metal hydroxides like NaOH and CaOH2 are alkalis. They contain the metal ions Na+, Ca2+, and OH- ions. The attraction between the metal ion and the OH- ion constitutes an ionic bond. But the bond in the OH- ion is covalent. Salts of oxoacids. Oxoacid anions like SO2-3, NO-3, and SO2-4 contain covalent bonds. But their salts and metal ions are formed by ionic bonding. Ammonium salts. We have learned that NH4 ion contains covalent and coordinate bonds. But its salt with any anion, example Cl-, CO2-3, NO-3, or SO2-4 will contain an ionic bond between the cation and the anion. Ammonium salts, therefore, contain all 3 kinds of bonds. Covalent bond. Some elements neither lose nor accept valence electrons. These elements achieve the stable electron configuration of a noble gas by sharing electrons. This pair of shared electrons forms a single covalent bond. A set of atoms linked together with covalent bonds is called a molecule. For example, when 2 hydrogen atoms move towards each other, their outer electrons start to get attracted by nuclei of each other. As you can see, the electron density shifts towards the center between the 2 nuclei. Hence, the covalent bond is formed. The bonding forces between the atoms result from interactions between the shared pair and the positively charged hydrogen nuclei. By sharing electrons, the atoms achieve the configuration of noble gas helium, since the 2 electrons are counted as belonging to both the atoms. A covalent bond is represented by a line linking the atoms. These are various examples of covalent bonds. Lewis representation of simple molecules. Now let us learn about the Lewis representation of simple molecules. The Lewis structure is used to represent the covalent bonding of a molecule or ion. For simple molecules, the most effective way to get the correct Lewis structure is to write the Lewis diagram for all the atoms involved in the bonding and then add up the total number of valence electrons that are available for bonding. For example, oxygen has 6 electrons in the outer shell, which are the pattern of 2 lone pairs and 2 single electrons. However, if the electrons are not placed correctly, one could think that oxygen has 3 lone pairs, which would not leave any unshared electrons to form chemical bonds. 4 unshared electrons are placed around the element symbol separately, while electron pairs are formed using the remaining 2 outer shell electrons. Lewis representation of simple molecules. Let's draw the Lewis structure for beryllium chloride. Now, beryllium is an alkaline earth metal and has 2 valence electrons. Chlorine is a halogen and has 7 valence electrons. That sums up to 16 electrons. As this molecule has 1 beryllium atom, so it is considered central atom, and chlorine atoms are drawn around it as shown here. Now, draw single bonds between the atoms. These 2 bonds signify sharing of 4 electrons. Now 12 electrons remain. As beryllium has 2 electrons and both of them are shared, so the rest 12 electrons belong to both chlorine atoms. Draw 6 electrons each on the chlorine atoms. Let's check if all the atoms have attained the noble gas configuration. Chlorine has 6 plus shared electrons, that is equal to 6 plus 2, 8 electrons. Similarly, for the other chlorine atom. Now, you should note here that beryllium has 2 plus 2, that is 4 electrons. Hence, you may want to make it a double bond between the atoms, but that is not possible, as chlorine cannot share more than 1 electron. Let's draw Lewis structure for aluminium chloride. Now, aluminium has 3 valence electrons. Chlorine is a halogen and has 7 valence electrons. That sums up to 24 electrons. As this molecule has 1 aluminium atom, so it is considered central atom, and chlorine atoms are drawn around it as shown here. Now, draw single bonds between the atoms. These 3 bonds signify sharing of 6 electrons. Now 18 electrons remain. As aluminium has 2 electrons and both of them are shared, so the rest 18 electrons belong to the chlorine atoms. So draw 6 electrons each on the chlorine atoms. Let's check if all the atoms have attained the noble gas configuration. Chlorine has 6 plus shared electrons, that is equal to 6 plus 2, 8 electrons. Similarly, for the other chlorine atom. Here is a similar case like beryllium, where aluminium has 6 electrons. Let's draw Lewis structure for carbon tetrahydride or methane. Now, carbon has 4 valence electrons. Hydrogen has 1 valence electron. That sums up to 8 electrons. As this molecule has 1 carbon atom, so it is considered central atom, and hydrogen atoms are drawn around it as shown here. Now, draw single bonds between the atoms. These 4 bonds signify sharing of 8 electrons. Now 0 electrons remain. Let's check if all the atoms have attained the noble gas configuration. Carbon has shared electrons, that is equal to 8 electrons. Similarly for the hydrogen atoms, leading to 2 shared electrons each.